Thank you, Adrian. Thank you, Adrian. Take your Tony. There goes the clock. Okay. So I'm going to stand up here, mostly because I injured my knee a couple months ago, and I want to hold on to something in case I fall over. But I'm glad to see you all this morning. Thanks for coming. Thanks for this invitation. I really appreciate this opportunity. Reflecting on this conference, it just sort of, for me, it brings together an awful lot of threads and themes and sort of movements across the data field over many years. Certainly, we think about the cognitive aspects of AI, which were being birthed over decades ago and now coming to fruition. We're also seeing just large amounts of data collected everywhere. We're seeing very smart engines like deep learning, and Watson is an example of deep learning across data. So we're seeing many different threads. But the thing for me always was about sort of the connections about things, finding connections. And I guess I was sort of a born scientist because when I was a child, I was always sort of seeing connections between things. And so for me, it's all about connections. And for me, it also is a chance at this conference to sort of step back a second from what I'm deeply embedded in, which is finding connections in data, finding patterns, trends, new knowledge based upon connections in data, to realize that there's different ways that we express those connections and that information, that knowledge which is embedded in our data. And so when I saw the announcement here come out, I mean, I was already being in conversation about being speaker here, and then I saw this list of topics, and I said, these are all the things that I love to talk about, love to ask my students to work on, because that's what you do, right? So these are the kinds of things I love. And so the stepping back moment happened for me. It was sort of started to happen a couple years ago when I was giving a talk on something related to graph analytics. And if someone came up to me afterwards and said, "You talk like a librarian." And I said, that's a great compliment, because that's sort of the role I had with NASA for 18 years, is sort of curating all these 15,000 space science data sets for the research community to use, access, make discoveries from these NASA data. And so for me, it was a compliment in a way, because I felt like if I had a second life, I would come back as a librarian or something like this, because I really love information science. How do you find information? How do you find knowledge? How do you express it? How do you connect it? How do you help people find knowledge and find information, buried, in those volumes? So think about the volumes in a library, right? So there's a physical layout, but there's sort of a virtual layout. That virtual layout, which we used to call the card catalog. These things are connected through authors, through publishers, through years, through topic categories. There's all these sort of ways we organize information and knowledge. And that's the kind of thing we need to be doing with big data. And I hate to use that phrase, so I just get it out of the way here. Okay, what we do with these large data collections is limited by our ability to actually find what we need and to know what's in there. And so what I like about smart data and graph analytics is the ability to make those connections, so that when you're looking at one thing, you can say, wow, here's something that's related to this. Here's something that's connected to this. Here's something that gives me more knowledge about the domain I'm exploring. So when I looked down this list, I said, these are the very things that I love to talk about. So I'm going to come back to the library science a bit at the very end. But in thinking about that, I realized that I was sort of blending a lot of different things in my own head that didn't come out very succinctly when I speak with people. So there's one way that we join data elements, and that's just doing a data join, right? So a data join is, okay, I have some social media data here, and I have some purchase records of my customers there, and these two things, in a sense, they don't necessarily relate to one another, because they might be different people. But I discovered that there are certain types of people who talk about certain products, and then I have customers who buy those kinds of products, and those same people who talk about those products are talking about other things that they like, so maybe my customers will like these other things too. So there's really no connection in the people there. Okay, so that's essentially a join, even though there's a little bit more of a sort of a topical connection there. But sometimes when we join data sets, we don't even know if there's any relationship between two data sets. We just combine them to see if there's a pattern. So there's joins that take place, and then there's also, as I mentioned, there's sort of graph models, there's the connections. Okay, so the nodes, are the entities, and the edges represent things they share in common. Okay, products they like to do, or things they like to do, or behaviors that they have in common. So the edge is a commonality between the two entities, which are the nodes. And then there's this thing called semantics. And I was sort of blending all these things together when I talk with people, and then I realized that I'm really talking about different things. So what semantics is, there's entities, but the edges are relationships. Okay, like one of my students is in the room. Pragan, where are you? There she is. So she is a student of me, I am professor of her. So there's a relationship. That's the edge, okay? So that edge is a different thing than when I do an SQL join across two columns or two tables in a database. Okay, so those are different types of connections, but they're all about doing connections. And so I want to talk about this in terms of what is very natural for us as humans to do. This is a short outline of what I'm doing today. So we're going to first talk about data, then big data, then smart data. So what do I mean by that? It's making these connections. So when we first saw our world and started exploring our world as humans, we asked questions. Okay, what if? Why is that? And I love this little switch here, so I'm going to tease you for a second here. All right, so here's the map of the world, and then, of course, you can say there's connections here. And people talk about this ancient continent which may have existed called Pangaea. So all the continents were together, then they split apart. They were connected. Okay, so how did people come across this? Well, they saw these patterns in the shapes of the continents, and they said, gee, these sort of look like they would fit together. All right, so humans are always finding connections, always asking questions, making connections, and then asking more questions. So when people say, how did we get to big data? It's this vicious cycle that humans have, right? I want to understand this, so I collect evidence and data to understand it, then that leads to new questions, so I go and ask more questions, which lead to new questions, I go get more data, and this is an exponential growth. All right, the amount of questions I have is proportional to the amount of data I have, therefore the number of experiments that I create to answer those questions is proportional to the amount of data I have, and off it grows. But the exponential growth problem is not the one that really is the challenge, it's the combinatorial growth problem, which doesn't get any play in the media, I guess, because it's just too many syllables or something in the word combinatorial or something. But I actually stood up in front of a room full of business people, technologists, like CIOs and CTOs of companies in a big conference a few months ago, and I made this statement, and they were just sort of like a lot of blank looks on their face. So hopefully I'll do a little bit better with you this morning. And so combinatorial growth is looking at all the possible combinations of things. Okay, so all possible combinations is a very large number, which people just can't appreciate. Okay, so if I just have 13 things, okay, I have 13 pieces of data, all right, if I have linear growth with my data, let's say it doubles, every year or so, that I go from 13 to 26. Okay, so that's linear growth. Well, we don't have linear growth. We think about exponential growth. Okay, so instead of having 26, I have 2 to the 13th, which is 8,000. All right, but if I have combinatorial growth, I want to look at all possible combinations and pairings of 13 items, which is nothing, right? I mean, you could probably write down 13 pieces of data, write 13 things, find all possible combinations. You have 13 guests coming to your house. You want to set up all the possible arrangements of the seating arrangements. If you think about the 13 factorial, that number is a huge number. All right, how huge is it? Let me give you an analogy that helps you understand. It's a very large number, but analogy is if I were to take 13 steps, 2 feet each, okay, so if each of my steps corresponds to a linear growth in my distance from this podium, so I'm not going to walk them, okay, I would be 26 feet away. But if somehow I had an exponential growth engine, so every step I took, my distance grew exponentially from this podium, okay, so after 13 steps, I'd be 2 to the 13 feet away from this podium. Well, how much is that? That'd be like walking around that lake out there, walking around the lake 4 times. All right, that's quite a bit different than from here to that table right there. All right, that's exponential growth. But what about combinatorial, 13 factorial? Well, that would be like if every step my distance grew combinatorially from this podium. After 13 steps, I would have to make 125 circuits of the Earth. That's a lot, okay? So if you think about how many types of inference, how many pieces of knowledge, how many connections can you find in a data set, it's growing combinatorial, and it's getting even worse as life goes on. So this, for me, is sort of the synthesis of what I would put under one broad umbrella of smart data. So we call it a smart data conference this week. And so when I was first invited, I said, what does smart data mean? I just started listing all the things that it means to me. And then I started looking at the conference agenda, and I said, yeah, people are talking about all these things this week, and so that's really great because this is what we mean by making our data smart? Okay, deriving intelligence, deriving knowledge from our data. It's the links between things. It's those graph databases. It's using machine learning to infer things. It's using cognitive analytics. Okay, sort of the ability of that human, again, looks at the data, looks at the world, and asks new questions. All right, so people say, what is it that Watson did in that game of Jeopardy? What is the game of Jeopardy? The game of Jeopardy, as you probably know, is a game where you have an answer to a question within some category, and your job is to come up with the question. Right? You only get points if you ask the right question for which that is the answer within that category. All right, so what is that? The answer is like your data. The category is like the context around your data. So what's the right question I should ask of my data in this context? That's your cognitive analytics portion. That's what the human would do. It's not what an SQL query does. It's what a human does when they look at something in a context of, what does this mean? What is all this? So using that to enrich our data, and then adding that as context metadata. So this is the librarian in me now. So enabling discovery from data by now adding that contextual data as a piece of metadata to the data, so the next time someone is searching for an answer to that type of question, and you found it, you can tag your data accordingly. So we provide all of this way of looking at our data, so ultimately we end up with this, in this world we live in, collecting data about everything, this 360 view of our universe, of our customers, of our entities, of whatever it is we're working on. And so a lot of times we express these things formally, like in ontologies, or informally, like folksonomies, which are just very informal ways of sort of the language of the people. How do people describe this? Then we can tag and annotate those things. And again, I'm very big on this way of indexing data. So find me all the things that people declared was a person of interest in my database. Find me all the events that someone once have declared behaviors of interest in my database. Okay, so I like this POI and BOI sort of analogy, persons of interest and behaviors of interest, or patterns of interest. Okay, don't just know that they're there, tag them accordingly. So when I was working at NASA for many years, there was a NASA Earth scientist who was doing really cool stuff way before his time. He was using Bayesian models to basically classify scenes and satellite imagery. So satellite images come down. There's thousands of them that come every day, many terabytes of data. And it's just like this massive repository. How do scientists get in there to find interesting stuff? Well, scientists are very focused on their research problem, whether it's dust storms or drought or floods, climate change, sea ice, whatever, but not missing maybe the bigger contextual picture because there's too much data. So what he did is he used these Bayesian classification techniques to tag images. So this, for example, this image contains a cyclone. This image contains a plume from a volcano. This scene contains an example of a landslide. This scene is an urban area. This scene is forest area. This scene is a seashore. So now people say, find me all scenes that contain this, this, and that, and you can now query and get images and scenes back, actually cutouts from the whole big data set. You just give me the cutout of the thing that I'm interested in. So that type of tagging and annotation enables the science to do their job, enables discovery, even though you might say that's a library function. Hey, again, that connectivity is all about what we're doing with our data, both for discovery purposes of data and discovery of knowledge. And so one of the things that people often overlook also are the breadcrumbs. So the breadcrumbs, that was one of the things that we thought about a lot when I was in NASA days, is we follow what people did, follow the links that they follow from on our website, see where they go, see what they're doing, and then we can improve their use of the data set, their use of the data repository that we had by seeing where people end up. Okay, so we in the same way that people do web analytics to understand sort of how did people land on my landing page, what were the search words, what were the keywords, and that's a really big business, right? Keywords. How did people end up at my site? And so, think about our data sets, see how people use it, and use those user trails as ways of improving access to your data. Because the next time a user comes in trying to do the same thing, you could make a recommendation. Hey, maybe you should look over here because that's where you're going to end up anyway. So let me send you there right away. So this sort of connectivity of data and knowledge is what our brain does, as indicated in the little graphic there. Is that this is the way we work in our world, all right? So William Shakespeare said, all the world is a graph, right? Well, not exactly, but anyway, all the world is a stage is what he said. But the natural data structure of our world is not rows and columns, right? That is not the natural data structure. The natural structure of the world there are things and they're related to other things, whether it's people or places or whatever. It's the connectivity, it's the relationships. That's the natural data structure. So the graph is the natural data structure. So that should be the natural way that we store our data, record our data, and work with our data. And again, going back to my 3 types of joins, again, sometimes joins are just, here are 2 data sets, let's see what kind of patterns I can find, joining them. And sometimes it's a graph model, again, where the edges are the shared features of the entities, the nodes. And then there's also the ontologies, the semantics, which are the edges of the relationships between the nodes. Okay, so all of those things are part of that graph model as I see it. Okay, so maybe it's not what we formally mean by a graph analytics model, but I want to think about this more broadly. The smart data is everywhere. So this combinatorial explosion we talked about, taking 13 data sets, and it will take you, I actually figured this out once. So my student, Pragan, sitting here, she worked with the Sloan Galaxy database. And so there's hundreds of attributes. We have over 450 attributes of galaxies in this database. And if we just took 26 of those attributes, which are the sort of a core set of interesting properties, colors, shapes, sizes, distances, things like that, if we just took 26 of those properties, all right, going back to my linear exponential combinatorial growth problem, if you looked at all possible combinations of those 26 attributes, just look at all those feature spaces and subspaces of all these different features, 2 dimensions, 3, 4, 5, 6, up to 26 dimensions, to try to find patterns, correlations, principal components in that space. 26 factorial combinations. If you had the fastest computer on planet Earth, and you could do a principal component analysis in those 26 dimensions for those 100 million galaxies in one, if you could do one of those PCAs in a nanosecond, okay, you could do one of those 26 factorial combinations, a PCM that in a nanosecond, 1/1000th of a second, for those 100 million galaxies. To do all 26 factorial combinations would take you the lifetime of the universe, even doing 1 per nanosecond. Okay, so even something, a relatively trivial data set, we have to be very, very smart about how we work with it. So we're not just going to do blind combinations. Obviously, we understand this connectivity, relationship, association, and things, so that's how we narrow it down. So our Internet of Things that's coming along is going to make life even worse, because now we're not going to have 26 nodes, we're going to have 50 billion nodes or 50 trillion nodes, depending on whether you read Gartner or Forrester or whatever. I mean, there's going to be a lot of nodes in this graph. All right, so there's a sensor measuring something. Each one of those sensors is measuring something. Think of that as a data node. And how does that relate to the data that I'm detecting from this sensor, from that sensor, from this, from that, from this? All right, so it literally is going to blow our mind. So I'm not going to say I have a solution today, but one of the solutions is the old moniker, or the old phrase of moving the algorithm to the data, move the code to the data. And so the closer you have your algorithm to the point of data collection, the better, because now you can not necessarily collect the data stream, you can collect the properties of the data stream. So, okay, that's edge analytics. So let me give you an example of edge analytics. Suppose you have a stream of data, and I'm going to keep it very simple, some kind of a time series. So this time series, you can measure, if you want, you can use something like a fast Fourier transform. You can do sort of simple statistics, mean, median, mode, skew, kurtosis. So you can do moments of the distribution of data points. So you can collect a handful of parameters, maybe 10 of them, 10 numbers, and track those 10 numbers, even though you have trillions of numbers coming at you. So let's just pick very simple. You have 10 components that represent the power, the features, the structure of that data stream. And so as long as you monitor that and those features don't change, those 10 numbers will forever represent that data stream. But if something changes, that is the stationarity of the system changes, that all of a sudden the mean starts shifting, or the variance starts exploding, or something different is changing, now that's the signal you want. The signal you're looking for is not this signal, trillions of data points doing something. It's the fact that the variance has suddenly changed, the mean has suddenly changed, or suddenly there's 2 populations there, the kurtosis suddenly plummets, which means now you have basically a 2-peaked or multi-peak distribution when you used to have 1. Anyway, so all these ways of monitoring your data at the point of data collection is going to help us to manage this flood. So there's smart data applications all across these, and you've probably been looking at the slide while I'm talking, so I'm going to move on from that. So in the interest of time here, I want to just mention things that we all know about machine learning, just because this leads to my next slide, which is more about the contextual smart data aspect. Okay, so I give a longer talk on this slide usually, so I'm not going to belabor with something you already know, but think about discovery from data, sort of these four categories. Okay, so there's class discovery, finding the patterns, for example, that diagram in the upper left, which astronomers call the banana diagram. So see the banana in the middle? Okay, so we see these clouds, these clusters in our data. As we add more data, we see the structure better and better and better and better. We understand better and better each one of those clouds, each one of those clusters, each one of those classes of behavior, and we start seeing new classes of behavior. Okay, so we do class discovery, we do correlation discovery, we find the correlations and patterns and trends in the data, so that leads to predictive power discovery. That is, if we know that X and Y vary with each other a certain way, given a certain X, you can find a Y. Okay, so that once you find a correlation, X becomes a surrogate for Y. But that's also what's called, there's also here prescriptive power discovery, and that is if you have many, many different dimensions. For example, here we see data cloud 2 has a certain correlation, and then it suddenly becomes a stronger correlation. So it's sort of weak in parameter 3, then it becomes strong in parameter 3. So at a certain place in the P1, P2 space, there's a sudden change in the upslope of P3. All right, so that's that tracking I'm talking about, the edge analytics. Okay, so now I know if P3 is something I can control, that is customer purchases or engine efficiency in my shop or supply chain optimization or something, I know that if I establish conditions P1 and P2 to be just right, I can achieve a better outcome. Or if it's something that I want to minimize, like a risk function, then I know I can move to another part of the P1, P2 space and get a lower value of P3, which is my risk metric. Okay, so that is prescriptive analytics because I know now what are the conditions I can set and change to achieve a certain outcome in some other key performance indicator. Okay, so we have that. We have novelty discovery, surprise discovery, sometimes called outlier detection, but that's so negative, I hate that. Okay, so surprise discovery is finding the surprising things in your data, and I can give you another lecture on that, which I won't today. But and then last on this list, but not least, of course, for this conference, is the graph discovery and association discovery. So this leads us to these 5 stages, as we call them, of analytics maturity, going from basically saying what has happened in the past, which is traditional business analysis, okay, hindsight or descriptive analytics, to moving to what's going on right now, which is diagnostic analytics, what's happening right now. So we go from hindsight, okay, to oversight, and then predictive analytics, which is foresight, predicting what will happen next. Okay, so sometimes when people talk about advanced analytics, they stop right there. They talk about, we're going to build predictive models of risk and customer churn and employee churn and da-da-da-da. Okay, so, but there's more than just predictive, and like I said, there's also prescriptive, which is given all the conditions. Okay, so if all I have is 2 parameters, X and Y, I can't really do prescriptive analytics, right? So it's like predicting the stock market for a given single stock. All you can do is some kind of auto regression. Okay, so all I can do is basically predict something that it's seen in the past. It can't predict a new tipping point or a new completely stated behavior if it's never seen it before. But if you know under certain conditions, given all the other contextual data that you've linked to, your smart data, now you can understand if I ever see these conditions again, then this particular thing will behave in a different way than I've ever seen before because I know that's what happens under those conditions. That's prescriptive. And then we get to that cognitive thing. Okay, so we're going from hindsight to oversight to foresight to insight, prescriptive, insight into your system, to what I call, with the play on words, I had to come up with something, so I called it the right side. Cognitive analytics is asking the right question at the right time in the right context with your data. Okay, so that's the game of Jeopardy again. Okay, knowing what the next best move is the right thing to do. That's cognitive. Okay, so that's being smart about your data. So in case that slide went by too quick, I wanted to give you a very quick mathematical and philosophical distinction between predictive and prescriptive. And it really bugs me when I read articles a lot of times that they just sort of roll together. People say, hey, we're doing predictive and prescriptive analytics. Like I see these talks at technology conferences, and it just rolls off the tongue. Yeah, we're doing predictive and prescriptive. And I don't think people really know what they're saying. Maybe they really are doing it. I'm not denying that they're doing it, but it seems to roll off too easily without thinking about it. And in fact, I've seen it, even people use a description of predictive modeling and put at the top of the article prescriptive analytics. And I said, that's predictive analytics, people. So I'm going to give you 2 ways of remembering distinctly how these are completely different. So again, predictive, given the set of conditions, what will the future be? So given X, find Y. Prescriptive, given Y, find X. Right? Given what I want to achieve, what are the conditions I must set? Okay, again, that requires many different variables, many different features, many different signals, many different inputs to your decision making, many different data sources to your decision making. Again, it's not a one-dimensional X versus Y problem, it's a multi-dimensional problem. Smart data again. All right, so to me, those two things sound completely opposite to one another mathematically. Given X, find Y. Given Y, find X. They are not the same. Okay, so remember that next time someone blends those two. But if you want something a little bit more philosophically based, I actually searched high and low to actually find what philosophers had to say about these two things. And so I actually found a statement by Confucius. So I think Confucius was the world's first predictive analytics person. He said, study your past to know your future. I mean, isn't that what we do? We look at the training data, historical data, to predict what will come next. Study your past to know your future. But I had to look really, really hard, but I finally found a philosopher who talked about prescriptive analytics. So some people will know this guy. He's a very famous American philosopher. His name is Yogi Berra. He says, the future ain't what it used to be. That is, instead of just predicting an outcome, that's the whole point of prescriptive analytics. Not only do I predict something will happen, but I don't like what I see is going to happen. I want to change it. I want a better outcome. I can predict employee churn or customer churn, but let me do something to keep that from happening. So as an astronomer, I work on projects where we're tracking asteroids to see if we're going to find the next killer asteroid that's going to wipe out civilization. How would you like it if the astronomers stood up and said, okay, we're going to predict the world will end next Tuesday. Bye, have a nice day. Oh, wait a minute, come back. What are you going to do about it? Okay, so we want a prescription. Like the doctor said, oh, you have cancer. Well, have a nice day. Well, wait, can't we do something about it? So we're all about doing prescription. Okay, so context is king in all of that. That is, this is the librarian in me coming out, but it's also how we navigate our data, make sense of our data, find knowledge in our data. The context, it's all about metadata. So one of my lines in my class to my students is the three most important things are metadata, metadata, and metadata, right? So metadata is data that describes data. It's other data from other people that describes your data, and it's your data that helps describe other people's data. So all these ways help us to become smart with our data. So the last minute and 50 seconds, I was going to tell you some data stories, but obviously I can't do that in 90 seconds. So one way you can tell your data stories is with your customer journeys. Okay, so there's a lot of talk now about customer journeys and using, again, multiple data sources to get that 360 view, see what all the touch points are of your customer, and understanding what customer journey is. So part of good storytelling is understanding one another, understanding the language of one another, which is where ontologies come in. So what happened there? There it goes. So if you can read the top green line there, it's supposed to be a joke. Three SQL admins walk into a NoSQL bar, but they walk out because they couldn't find a table. If I told this joke to my family, they would have no clue what I'm talking about. And I've told statistics and data jokes to my family, and they have no clue what I'm talking about. So we understand the context of data. And so I taught a whole lesson on semantics in my class, and I had my students memorize this line. Okay, so I start off the lecture saying, by the end of this hour, you'll be able to close your eyes and tell me that an ontology is a formal, explicit specification of a shared conceptualization. Are you smiling, Debbie? An ontology is a formal, that is a committee, a group have agreed to it, explicit, we put it down, it's a specification, that is it's defining something. Of what? A shared conceptualization. So a conceptualization is, for example, a conceptualization is, what are the words that we use, like tables and NoSQL, no tables, whatever. We understand what it means, but it's not just I understand it, but we understand it. It's a shared conceptualization. So an ontology is a formal, explicit specification of a shared conceptualization. So my students think I'm crazy when I say this, that they'll be able to close their eyes and repeat this definition by the end of the lecture, and they can do it, because once you understand all the words there, it makes sense. All right, so if I say there's going to be I tell my students, hey, what if I tell you there's a party at 7 on Saturday? And then Monday comes and people said, gee, you weren't there. Why weren't you there at 7? I said, well, I forgot to tell you 7 a.m. Oh, wait a minute, our shared conceptualization, when you say party at 7, you mean p.m., right? So it doesn't work if you don't share the conceptualization. So semantic facts are these triples And I wanted to tell you this great story of one of my other students. So I'm going to skip that. But the idea is that sometimes in transactional databases, we miss the most obvious thing. And so one of my students, which was the previous slide, but I'm not going to focus on that slide, he was looking at the semantic expressions of content topics of discoveries in the medical research journals, 23 million articles in the, I'll go back, 23 million articles, over 26 million, 80 million RDF triples expressing the medical concepts across all these different fields of medicine, and trying to find maybe perhaps new discoveries in the medical field that are missed because there's no connection between journal article A and journal article C. Okay, 1 and 3 have no connection, so scientists have completely missed it, but there's a shared concept in the middle that connect the two. So we know all about this in graph modeling. We know all about this when we talk about link distance, but if you do normal term frequency distance, the distance between 1 and 3 is infinite because they share nothing in common. So topic frequency, term frequency says there's nothing there. So this completely breaks the triangle inequality. Distance from 1 to 2, small, 2 to 3, small, 1 to 3, infinite. All right, so here's my world here. Okay, so this not just happens in medical research, it happens in marketing attribution. That is, somebody told you, then you bought. So there's someone in between. It also happens in money laundering and cyber networks, fraud networks. There's a middle person. So person 1 deals with good people. Person 3 deals with good people. So they must be good people, right? Oh no. If we ever saw a connection between 1 and 3, we would arrest them because they should never be exchanging money that way. But they do it through money laundering. All right, so that's a money laundering example, but we're doing medical research discovery using the exact same concept of finding articles that are infinitely far apart, or very far apart in the term frequency topic space, but not in the link space. And so the last slide, get smart about your data. Don't just, as one friend said, just don't kick your big data problems down the road. Get smart about your data. Collect, connect, and curate this knowledge. Create knowledge, not databases. Thank you.